All right, so today we're going to start with a couple other historical numeration systems. The first one we're going to look at are the Babylonians. The Babylonians have a nice system in the sense that it's condensed. There are only 2 symbols. Can you guys see the screen okay with all the light coming in? No. Okay. Mason, can you stop texting for me and put it away and change some of those screens? In fact, Michael, can you do this one? And Mason, can you do this one? Just twist them a little bit. Maybe even, yeah, can you do that one for me, Matt? Let's see if we can get the glare off. Oh, that is better, isn't it? Okay, good. All right, so they have a nice system because there's very few symbols. That part of it's nice. The symbols are a little bit, they look very similar to one another. They have a symbol for the value 1 and a symbol for the value 10. Okay, so they only have 2 symbols. Okay, so yay for few symbols. The symbol for the value 1 looks like a triangle where its point is down. Okay. They draw theirs filled in. If you don't fill them in for me, that's okay. I mean, if you want to draw them so that they're empty, just for a time-saving issue, that's fine. The thing you have to be careful of is that they don't start to look like the symbol for 10 because they are very similar symbols. They're very triangular looking, but this one almost looks, I don't know, kind of like a boomerang or like a little bit of a filled in less than sign. If you want to shortcut this, you can draw it as a less than sign, and I'll be okay with that too. Okay, so either of those sort of notations for it, I'll work with you on that. Okay. So jot down these last 3 pieces of information because they're important. They repeat symbols. Okay, I mean lots of systems did that, right? The Egyptians did that. The Romans did that. Chinese didn't repeat symbols, but the Egyptians and the Romans did this repeat symbols business. The big difference is part number 2, where the positional base is they have a positional base 60 system. We haven't had any base anything else, but in fact, most of ours haven't even had really bases. We've kind of had this positional system with the Chinese, where they kind of grouped things together in a way with base 10 stuff. That's the closest we've had to this. We had everything sort of hinged upon the number 10 in the Egyptians as well, and we kind of hinged on the idea of the place values as we understand them with the Romans. So nobody else has this weird base 60 business going on. The other issue, and this is a big issue, and we'll see it, I'll show you where it comes into play as being a big issue, is they do not have a number for the number 0. Okay, so in fact, only one system have we seen did have a number for the number 0. What system had a 0? Hindu-Arabic does, but it's somebody else. Chinese. Do you remember it? It was the really exciting symbol that I can't draw very well, and every time you guys looked at it, you were like, how many lines are where? Okay, it was a funny-looking symbol. Nobody else so far has had a 0, except for us, of course, our system, and the Chinese. So they lack one here as well, and in their system, especially, it's a problem. For the Roman numeration system, it really wasn't problematic that there wasn't a 0 because of the way they structured their system. It wasn't necessary. I mean, okay, but for the Babylonians, it's going to be a problem. All right, so here's the first ones we're going to do. You notice some stacking going on. Stack them, don't stack them, I don't care. But this is the first 2 we're going to do, and we're going to take this and we're going to turn it into our system. So jot these guys down first, and then we'll work through them together. You have no idea how long it took me to get those looking so nice. They look pretty good on the screen, don't they? They're not going to look so good when I draw them freehand for you on the next slide. Okay, so one of the things that they'll do is they'll put 10s before 1s, so a larger number before a smaller number. So if you ever see a smaller number turn back into a larger number, which you see that right here, correct? There's a triangle followed by the little boomerang less than shape. So a smaller number, which is a 1, followed by the larger number, which is a 10. When that happens, you for sure have changed place values. So this breaks this apart. When there's a smaller number, because this is a value of 1, in front of a larger number, this is a value of 10, you for sure have changed place values. Okay? Now, you might also change place values otherwise, but the general assumption that we're going to have is that that's when we're going to know that we've changed place values, and otherwise we're going to assume we didn't. All right, so we've got 2 place values here. I've underlined each of them in pink. Okay? What I first want us to do is to just count how much we've got in each place value, and then I'll tell you how we deal with the place value issue. All right, so how about before the first vertical pink line? What is that? 21, that's right. And afterwards? 22. Okay, everybody good? Okay. All right, so what does that mean? Well, in our system, we have place values of 1, and the second place value is worth 10, and our third place value is worth 100. So if we have the number 342, then we mean we have 3 hundreds, 4 tens, and 2 ones, right? If they have the same thing going on, it's just that they don't have a ones place and a tens place and a hundreds place and a thousands place. They have a ones place and a 60s place and a 60 squared, because that's how we actually get our 100, is we do a 10 times 10, or 10 squared. So these are actually powers. Let me write it that way for you on ours. Our system is actually based on powers of 10 because it's a base 10 system. Their system is a base 60 system, so it's based on powers of 60. So in their place value system, this place is the ones place, just like before. And this place is the 60s place, because it's a base 60 system. Okay, so far so good? Now, going back to my example with ours, I had in here 342. What that means is I really have 3 hundreds. That is, I have 3 times 100, right? Imagine like having money, right? If I have $300, it means I have 3 $100 bills, or at least that's one way we could do it with our currency, correct? And I would have 4 $10 bills, and I would 2 $1 bills. Okay, so imagine now that you're working in their system and they don't have a $10 bill, they have a $60 bill. Is everybody following with me? What this says is that I have 21 $60 bills. And then I have 22 ones. Okay, so taking this piece right here, what this means is that all of this, it means I have 21 $60 bills. So they're worth 21 times 60. I mean, that's what we do with hundreds, right? If I have 3 $100 bills, it's worth 3 times 100. That's $300. And then I have left over after that 22 that are each worth $1. So what is 21 times 60?
1,260.
Are you guessing, or is that what you've got in your calculator? Did you do it out? Laura, I saw you do your calculator. Is that what you have? Do you know? Sorry, I don't mean to put you on the spot. I just want to make sure that we've got it going on. Oh, I think that's right. I don't have all the details written out. 21 times 60. I think you're right, Tyler. 21 times 60. Did you get 1260? Okay. And then add 22, and what do we have? Perfect. So this is our number that's the same value as their number that we started with. Okay, there was more to this problem than in the last section, right? That base business actually changes a lot about how we do things. All right, the first thing we did, though, and we're going to go back and do it the same thing again on problem number 2, is we have to figure out where my places change value. And they always change value when I have a smaller number in front of a larger one. So, taking a look at this one's worth 1, this one's worth 10, this one's worth 1. So between these two right here, the second and the third to the last, they change place value. So draw yourself a line. You know that changed place value there, no question, because there's a smaller value in front of a larger one. It's kind of like with the Roman numeration. You know something subtracting is going on because there's a smaller value in front of a larger one. All right, so this one, the one here to the left of the pink line is a 1, and then I have a 10, and another 10, and then I have a whole group of 1s. Again, that's smaller than a 10, so I'm going to draw this line right here because it changed place value. Then I have these 3 1s, and then I have 4 10s, and that's all good. So how many place values do we have on this one? 3 place values. Let's figure out how much is in our place values, just like we did last time first. So starting on the left, what's that number? 43. Good. How about the second one? 21. And the last one? 11. Awesome. Okay. Now we already know this from last time, that the one on the right is the 1's place. And the second one, the one that's got a 21 in it, is what place? The 60. What's the third one going to be? 60 squared, which is 3,600, right? Yeah. So this is the 3,600s place. So again, let's try thinking about it with currency, because currency kind of is an easy connection for us. Because I don't know about you, but money's a good thing, right? Yeah, it is. Okay. So I have 11 $1 bills. I have 21 $60 bills. And I have 43 $3,600 bills. I know, that would be a funny bill. Okay? But that's what I've got. Okay? So what are we going to do to figure out how much money I have, or what this number is in our system? We're going to multiply. So we're going to multiply 43 times 3,600, which is 60 squared, plus 21 times 60, plus 11 times 1. You're going to multiply things, you're going to add things, and then somebody's going to give me a final answer for what this number is. Thank you, Stephanie. Okay, that's what I have too. And a couple of others you're working on that. Is that what we're getting? Everybody getting that value? Okay, I'll take the lack of response as an okay to continue. Are we good? All right. So think with me. To get from Babylonian into our system, we used what operation? Multiplication, didn't we? So what do you think we're going to do to get from our system back into theirs? Division. And I want you to write that in big and bold somewhere on your notes. That's an important thing. And here's why. Half of you are going to do it wrong on the test. You're going to use division when you should have used multiplication. You're going to use multiplication when you should have used division. Don't. Write it down. Okay, I will repeat it, you bet. So to go from someone else's system, anybody else's system, this is a true statement in general, anybody else's system into our system, we multiply. When we're turning things into base 10, Hindu Arabic, we multiply. But when we start with our number and turn it into somebody else's number or into some other base or some other whatever, we divide. So that's where we're headed on the next slide. We have two numbers in our system, and we want to turn them into somebody else's. So what operation are we going to use? Division. All right. I'm going to show you a very nice, not there yet, a very nice algorithm for the division. And not algorithm, that's not even the word I want. A nice organizational structure. What it is. It's just an organizational structure. So you know that this is Hindu Arabic into Babylonian, and you know Babylonians are in a base 60. And we know the first 3 digits in their place value, or their first 3 place values are the 1's place, the 60s, and then 60 squared, which is 3,600. And we can go larger if we need to. We can do 60 cubed just for kicks. Somebody tell me what 60 cubed is. 216,000. which is larger than either number 3 or number 4 is, right? So I'm not going to end up needing that one on this particular, either of these particular problems. All right, so here's what we're going to do. Whichever one of the numbers that you're dealing with is the largest number that will still go into the number we have is where we're going to start. So our number is 3280. The numbers we have to work with are 160, 3600, and then 216,000. What is the largest one of those that will still go into 3280? 60, isn't it? Okay, so the first thing we're going to do is we're going to divide, because we said we were going to use division, and we're going to divide by 60. And the division is going to start out looking like what we have. So write this down just like your old division you've used before. But then we're going to draw some extra pieces around this just to give the structure that we need. We're going to draw a line underneath the 60, kind of connects here. And then we're going to kind of put this into a box. I know it looks a little bit funny. I promise it's going to make sense more when we move into the next section of material. Maybe actually in 4.4. But we're going to need this structure later, so we're just going to use it now. Okay? Here's what we're going to do. You're going to take your calculator if you'd like, and you're going to say to your calculator, 3280 divided by 60. So somebody do that. And the answer I want, Stephanie, is the number before the decimal. What'd you get? 54. And you're going to put the 54 right here. Pause with me. So it's just the whole number part we're going to write down.
Do we need to round up?
No, no rounding at all. Okay? What we found out is that 60 goes into 3280 54 times. Okay? So here's what you should imagine. You should imagine in Babylonians you have 3,280 $1 bills. And I don't know if you're like me with our numbers even, but when I get, like 15 $1 bills, I don't want to carry around 15 $1 bills. I want to turn them into something that's going to take up less space. Are you with me? Okay, same idea here. We've got 3,280 $1 bills. We'd like to turn some of them into 60 so that we have less, to carry around. Okay, that's what we're doing. So we're figuring out how many $60 bills we could get out of this money. And we do that by dividing by 60. It divides evenly. It doesn't divide evenly, but it divides fully or completely into 54 $60 bills. Next thing you have to do, just like you did back in grade school, is you do 54 times 60. What is 54 times 60? 3240. So it actually took you 3,240 of those $1 bills to give you 54 $60 bills. Okay? So how many leftover $1 bills do you have? 40. And if you were talking about our bills now, we've got a 1, and we know that there are 40. And the reason I just did that last step looks a little funny right now. It will make more sense when we do part 4, problem 4. Okay? So what I end up getting down here is that when I divide by my last 1, I have the 40. Whatever the number is here is going to end up matching. So I have, in our system, or in their system rather, 2 place values. This is the 1's place. This is the 60's place. I have 54 of them in the 60's place, and I have 40 of them in the 1's place. So far, so good? I have 54 $60 bills, and I have 40 $1 bills. Anybody notice that I'm not done?
Yes.
I still have to draw some triangles and less than signs, right? I need to use their symbols. So now I'm ready to use their symbols to actually write out what 54 looks like. What does 54 look like? 5 of the less thans, right, for 50. And then 4 of the triangles for 54. You mean in terms of like how many less thans on top of something else? Or, no, there's not a specific structure. If you wanted to, you could write them all side by side, Alexis. So you could write out 5 less than signs and then 4 triangles. And then I need to write the number 40 out. How to do 40? 40 less than signs. And I'll stack them like that too, just because I already stacked things. So do you see the 50 and the 40? The 54 and the 40? So this is 54, this is 40, and we're done. All right, next one, number 4. Number 4 actually has a number that's big enough to divide by 3,600, right? So we're actually going to start with 3,600 on this one. So 3,600 goes the front, underlined, and we've got this bracket thing going on. with, sorry, the 43,205. Okay, so again, this is like me having 43,205 $1 bills. It would take up some space. I'm imagining the briefcase when somebody has a ransom thing, you know, like on television. And they bring the briefcase and they show you, and there's all these $1 bills inside, okay? Too many of them. I don't want to carry that around. So I want to turn them into the biggest bill I can, and the biggest bill I can turn them into is a $3,600 bill. Okay, so we're going to divide. I see Mason's dividing for me. Did you get a number, Mason, for how many times this goes in? Okay. You got 12? Okay. Tyler says 12.
Yeah.
Does it look good? All right, what do we do next? 12 times 3,600. So what is 12 times 3,600? Lynn, did you get one?
43,200.
Oh, that's nice, isn't it? Because that's almost all of it. Friendly. Okay. So the next thing I'm supposed to do is divide by the next bill smaller. And the next bill smaller than a $3,600 bill is a $60 bill. Okay. But what is 43,205 minus 43,200? 5. Careful. You actually did 5 divided by 60, didn't you? Okay, so the picture again is that I have 5 $1 bills. Can I turn any of them into a $60 bill? No, can't do it. So this is 0, and then we could say 0 times 60, and it looks a little bit weird, but just bear with me. We're going to put a 0 there for now. I still have 5 $1 bills left, so when I put the $1 bill on the outside, I have 5. So the structure for this is kind of nice because they put them on the same line, right? This 3,600, there's 12 of them. This 60, there's 0 of them, and this 1, there's 5. It reads really nice. All right, so I have 3 place values. 1, 2, 3. And in those place values, I have 12, 0, and 5. Okay, so it's the 1's place, the 60's place, and the 60 squared, or 3,600. How do I write a 12?
1 of the ones, and then 2 of the triangles.
Perfect. 1 less than 2 triangles. I don't write a 0, so I just don't write anything. Okay? And then how do I write 5 ones? Yeah.
I think I missed something when you were talking about the less than sign.
Yeah?
When you had, like, there's a less than sign with the, like, crescent
Mm-hmm.
thing on the side. Is that different than?
It's the same thing.
It's the same thing.
It's just I'm just shortcutting how I'm drawing it so that because I can never skim.
Distinguish that.
Oh, no, that's a great question. This is a problem, isn't it? Because there's 2 different things that could happen here, right? One thing is, what could this number be? That looks a lot like 17. And I don't know about you, but if I were a bookkeeper and somebody owed me $43,205 and they gave me $17 and said we're settled in full, I'd have a problem with that, correct? And yet the numbers look very similar. What else could it be? Now, some textbooks that I use will draw this, it's not our book, but some will draw this like this, with a space here. Or they might stack those last 5 up on top of each other. And if you at least do that, you can at least say that it's not 17. Agreed? But what could it be?
12,300.
Well, close. You're on the right track. So it could be 12 of the 60s as opposed to 12 of the 3,600s, right? So 12 $60 bills and 5 ones. This is not good. And this right here is the reason why that 0 was so important and we don't have one. If I simply had a 0 to stick in there, I could solve all those problems, right? Yeah. All right, so to answer Mason's question, how do we know? You don't, okay? So the answer is this. When you convert from their system into ours, you're going to draw those pink lines just like I told you. You're looking for the natural breaks, the ones that are for sure the right breaks, okay? So if I gave you this problem right here, the way we wrote it out, You'd tell me this is 17 and you'd be right. That's 17. Okay? The only time that it would be a problem is that when you turn it into that number and it looks like 17, you just have to realize that it doesn't look like what I think it should because there's flaws in their system. There's a reason we don't write in Babylonian. And this is just one of the reasons. Okay? Anybody have any idea, before we leave the Babylonians, why they might have done things in base 60?
There's less.
You would have to have less place values, and they had fewer numbers of symbols. People like to do nice things with 60s with triangles and things too. Remember 60 degrees is a perfect angle for a triangle, things like that. So that's part of it. We've got one more numeration system we're going to do, and it's our friends the Mayans. Gotta love the Mayans, because the world did not end last year, right? Yay, we're still here. You still get to do math. I still get to teach. It's great. If it had ended, it'd all be okay too, because I'd be in heaven and I'd be having fun there too. But it didn't end. So the Mayans, they actually have 3 symbols. One symbol is a dot. Okay. A dot for the value 1. One symbol is a line. It's a horizontal line for the value 5. And then they have a symbol for the number 0. And it looks like a shell. Let me figure out what your book uses for this shell picture. It almost looks like a football, I think, but something like that's how this book draws the shell. 3 symbols, and there's a 0, so that's good, right? That's good news. We got a 0. Maybe we won't have as many problems as the Mayans or as the Babylonians had. They write it vertically like the Chinese. Okay, same thing. Highest values, highest place value. So the value on top's the big number, and as you move down, the lowest number's on bottom. They have a modified base 20 system. Okay, so it's not base 10, it's base 20. It's not base 60, base 20. The word modified, I'll show you why in a minute. Okay, so, and then they use repeated symbols within the position like the Babylonians. So if they want the number 10, they're going to do 2 lines to give you the number 10. Okay? Here's their base system and why it's not exactly base 20. In their base system, they have the ones place, and then they have the 20s place, and I'm happy enough with that, but then things go a little wonky. Okay? The next one's not 20 squared. Sorry. It's 20 times 18. After that, they start putting powers on the 20. So 20 squared times 18, and then they would have 20 cubed times 18, and so on. Somebody's going to grab a calculator, you're going to do it in your head for me quickly, and you're going to tell me what is 20 times 18. Thank you. It is. It's 360. Okay, so we're going to have 2 discussions briefly. Number 1, why do you think they would have used base 20?
Circles.
The 360 has to do with circles. We'll get there in a sec. But why base 20? Drew, you gotta be my picked on person today. Come here. I could have picked on Mason too, I guess. So you see Drew, he has on sandals. And shoes are sort of a relatively new idea, right? So this is what my brother does. He always makes fun of me teaching. He tells me that I should tell you all you should not be able to wear shoes to class because you'll be able to do math better if you have your fingers and your toes to count on. That's what the Mayans did, right? They've got 5 on each hand. They've got 5 on each foot. That's a total of 20, base 20. Think through. All right, so that's why they've started with base 20. But then the 360 is what Clinton was talking about. 360. Why is that 360 important, Clinton? Circles. What about circles?
Naturally occur.
Okay, but what does the 360 have to do with a circle?
It's the points and degrees.
The degrees. That's what I wanted, the degrees. There's 360 degrees in a circle. So you have this idea of circles, okay? And what else does 360 sound awfully close to? The number of days in a year. And in their calendar, that's what they used. They used 360 days in a year. Okay? So maybe the world's still coming to the end because their calendar was a little bit off. Okay? All right, so that's what's going on here. I want to show you how we work with it, of course, though. And again, they have the Chinese, so we're going to work from the bottom up in the places, and we're going to do things vertically.
From the bottom up?
Well, or top down, depending on your perspective. The smallest value's on the bottom, though.
Okay.
Yeah. All right, so go ahead and jot these guys down. Don't they look beautiful? Again, not put on the spot. I can actually draw pretty decent dots and lines. I know. My claim to fame, I can draw dots and lines. Okay, so they do have one problem that looks a lot like the Babylonian problem. Over here when we did the Babylonians, I know I just changed your screen, I promise I'll come back. Over here, whoops, right here, when we did the Babylonians, we had to draw these vertical lines in, these vertical pink lines, and we recognized the fact that, in theory at least, we could have drawn that vertical pink line in other places in addition to the ones we drew, but we're just going to draw them where we know they have to be for sure. The same thing's going to happen over here with our friends the Mayans. We don't know for sure that there aren't any other sort of breaking up of place values that are not occurring that we can't see. But we're going to put them in where we know they occur. So let me show you how we do that. Okay, so they always have the dots on top of their lines. So anytime you see a line on top of a dot, the place value has to be different. So right here has to be a break in the place value because I have a line on top of dots. And that is the only guaranteed we have to break the place value there. So far so good? Dots always go on top of lines, so if you see lines on top of dots, I changed place value. Now, let's count. Above my blue line, what number is that? 4 dots and a line, so we got 9. Below my blue line, what do I have? 14. Everybody good so far? But we are working in base 20, which means that this bottom place value is the ones place, and if we go up from there, we get the next place value up. What's the next place value in their place value system? It's the 20s. So just like we did with the Babylonians, when we start with their number and we turn it into ours, the operation we use is multiplication. We are going to multiply the number times its place value. So that means we're going to take 9 and multiply it by 20, add that to the 14, which is multiplied by 1. So far so good? All right. What is 9 times 20 plus 14? 184? 94? Sounds good. 194. Now, you'll notice beautiful things in the next one in the sense that we've got a shell in there, right? Or whatever we want to call it, but I guess I didn't quite draw it the same way your book did at one point, but whatever. It's a shell. Okay, so just like with the others, okay, so if we change from a line to a dot, it changes place value. The shell actually holds a place value. It would let me, for instance, if I'd had a shell or something equivalent to it back over here in the Babylonians, it would have let me put something right here, right, to actually be able to know that there's a 0 missing. I actually have a place value and there's nothing in it. Okay, that's what that's going to let me do in the Mayans. So I know for sure my place value changes right here because I have a shell. It has to change around the shell without a doubt. So I'm going to have a line above the shell, a line below the shell. For sure has to happen. I also have a line underneath the shell and then a dot and then a line. Where do I know there's another change? Above the dot. Very good. Okay, everybody with me on that? You know, this is very unusual. We're going to write down the numbers in between all the blue lines. Above the top blue line, what number is that? It's 17. I've got 3 lines that are each worth 5 plus 2 more, so 17. Next number down is 0. I can do things all day with 0. I don't know about you. And then I've got a line all by itself, which is a 5. And then the number underneath, a 6. Now, typically speaking, when I get to a test, most of you will be able to do this. You'll write 17056, and then you'll tell me the number is 17,056. Okay, that's wrong, right? Because that means you've completely undone anything about the fact that it's base 20. Don't do that. This is in base 20. So this right here is the ones place, the 20s place. The next one was 20 times 18, which is 360. And then we actually have 20 squared times 18. And somebody's going to find out for us what 20 squared times 18 is. Thank you. It's 7,200. So these are my different place values, right? This is like me having a $1 bill, a $20 bill, a $360 bill, and a $7,200 bill. Okay, why those numbers? Seems a little odd, but that's the idea of what we've got going on. Same idea. Then what do? We multiply. So what are we going to multiply?
17 times 17.
Good.
Plus 0. Or do you have to have
I'll write it in just so that we remember we did it. 0 times 360, yeah.
plus 5 times 20 plus 6 times 1.
Awesome. That's a 1 at the end. It looks kind of funny, but. All right, so we're going to multiply, and you're going to tell me what you get. Excellent. Oops. Get the number right. So when Alexis multiplied, this is what she what she has, and it matches what I have. Does that look okay? All right. We have one more thing in this section, and we're going to do one of the problems, and then I'll let you go. Okay? We'll jump back in with the last problem next time.
So with those, we don't have to, like, okay, since they're already written in that form, we don't have to do the symbols. Right?
No, yeah. So you're taking it from their symbols into ours, but
Okay.
we're about to go the other direction. Okay, so you guys know from last section, that is the Babylonians, that we actually have to do division, right, on the next steps. And we do division with their place values. They have a 1's place, the 20's place, the 360's place, 7,200, and we can make it bigger if we need to, but we don't. What's the biggest number that goes into 208? It's 20. So I'm going to start out my division with 20. And how many times will 20 go into 208? 10 times. Very good. 10 times 20 is 200, with how many left over? 8. So there are 8 ones, and 8 in the ones place. All right. How do I write the number 10? 2 lines. How do I write the number 8? 1 line and 3 dots, and what goes on top? The dots. So I'm going to have dots on top of lines. So 3 dots on top of 1 line. And that'd be your final answer. So writing theirs in their system, dots and lines, I like that. That's easier, yeah. All right, just so that we know where we're going to start, what number are we going to start to divide us by? 7,200. Yeah, 7,200 is going to go into this. And if we try 20 cubed times 18, it's going to be too big, just so you know. But you should think about that and make sure it's not, because it is going to be too big. So we're going to do this one last one next time, and then we'll be finished with 4-2.